Hello guys, we want to start lecture 38. So in this lecture, we want to talk about solution of wave equation. In the last lecture, we talked about the wave equation and boundary value problem and the assumptions that we had. So today we just want to talk about solution of wave equation using separation of variables. So we want to solve one example. In this example, you want to solve the following wave equation. So the partial differential equation is second derivative, 4 times second derivative of u with respect to x is equal to second derivative of u with respect to t. So length of the string here is equal to 1. As a result, x is between 0 and 1. We have two boundary conditions. U of 0 and t is equal to 0. U of 1 and t is equal to 0 because the string is fixed at the beginning and at the end. And we have two initial conditions. In the first one, we have u of x and 0 is equal to sine pi x, and we have derivative of u with respect to t, or velocity of the string at t equal to 0 is equal to sine 2 pi x. And at the end, you want to find displacement of the string in x equal to 0.25 meter and t equal to 0.2 second. So in fact, in this problem, you want to find u of x and t, which is displacement of string. In order to solve this problem, we use separation of variable, and I'm going to follow the same algorithm that I already posted on Moodle. So at first, we assume that u of x and t is equal to some product of x, which is function of x, and t, which is function of time. Then I have to find second derivative of u with respect to x, second derivative of u with respect to t, and then plug in the partial differential equation. So second derivative of u with respect to x, it's equal to x double prime times t, and second derivative of u with respect to t, it's x times t double prime. Now I plug it in the equation, so as a result we have 4 times x double prime times t, it's equal to x times t double prime. So I can write it in this form. So x double prime divided by x, it's equal to t double prime divided by 40. So we have two functions. One of them is function of x in left hand side of the equation equal to a function of t in right hand side of the equation. We already said that the only condition that two functions with two variables can be equal. So these two functions should be constant. So I say they are equal to minus lambda. So we're gonna end up with two ordinary differential equations. The first one, x double prime plus lambda x equal to 0. And the second equation is t double prime plus 4 lambda t equal to 0. The next step, so we have to go through the boundary conditions. The first boundary condition says that u of 0 and t, it's equal to 0. So u of 0 and t is x of 0 times t of t. It should be equal to 0. We know that t of t cannot be equal to 0 because we're going to end up with trivial solution. As a result, x of 0 is equal to 0. And in the second boundary condition, we have u of 1 and t equal to 0. As a result, x of 1 times t of t, it's equal to 0. So t of t cannot be equal to 0. As a result, x of 1, it's equal to 0. So we could find two boundary conditions. Now we have to solve ordinary differential equation x double prime plus lambda x equal to 0. And we have two boundary conditions, x of 0 equal to 0 and x of 1 equal to 0. In order to solve this ordinary differential equation, we have to consider three different values for lambda. Lambda can be negative, can be positive, and can be equal to 0. So at first I start with lambda equal to 0. I assume that lambda is equal to 0. As a result, ordinary differential equation would be equal to x double prime, it's equal to 0. As a result, x prime of x is equal to a constant like c1, and x of x, it's equal to c1x plus c2. Now I have to apply the boundary conditions. So we have x of 0 is equal to 0. If I plug 0 in this linear function, so we're going to see that c2 should be equal to 0. And the other boundary condition, we have x of 1 equal to 0. If I plug 1 in the equation, so we're going to have c1 equal to 0 as well. So we have c1 and c2 equal to 0. It means that x of x is equal to 0. This solution is trivial solution, and we don't want to have trivial solution, so it's a trivial solution. But we are looking for non-trivial solution. As a result, lambda equal to 0, it does not end up with the solution in this problem. We have to consider lambda negative and lambda positive to see which one ends up with non-trivial solution. So I start again with lambda as a negative number. So lambda is minus alpha squared. Alpha squared is always positive. As a result, minus alpha squared is negative. So the partial differential equation would be x double prime minus alpha squared times x equal to 0. And solution of this ordinary differential equation is, so we use c1 and c2 here. I used c3 cosine hyperbolic alpha x plus c4 sine hyperbolic alpha x. Now I have to apply boundary conditions. So x of 0 is equal to 0. As a result, if I plug in this equation x equal to 0, so we have cosine hyperbolic 0 is 1, so we have c3. Sine hyperbolic 0 is 0, so it means that c3 should be equal to 0. And the other boundary condition says that x of 1 is equal to 0. If I plug in the equation, we have c4 sine hyperbolic alpha equal to 0. Sine hyperbolic cannot be equal to 0, sine hyperbolic of 0 alpha, because sine hyperbolic is 0 only at alpha equal to 0. As a result, in this case, c4 should be equal to 0. So again, we ended up c3 and c4 equal to 0. So it means that x of x is equal to 0, and its trivial solution as well. So we have a trivial solution. So it means that lambda cannot be a negative number. Let's go through the third case. In the third case, we have lambda is a positive number. So as a result, the ordinary differential equation is x double prime plus alpha squared x equal to 0. If you solve it, and see that x of x is equal to C5 constant cosine alpha x plus C6 sine alpha x. We have to apply boundary conditions. X of 0 is equal to 0. If you plug 0 here, we have cosine 0 is 1, so we have C5 plus C6 sine. Sine 0 is 0, so we have just C5. C5 should be equal to 0. And x of 1 is equal to 0. As a result, we have C5 already equal to 0. We have C6 sine alpha should be equal to 0. So C6 cannot be equal to 0 because if C6 is 0, we have C5 and C6 both equal to 0. We're going to end up with trivial solution again. As a result, we assume that sine alpha is equal to 0. Sine alpha is equal to 0. So alpha should be equal to n times pi. So we ended up with this solution. So x of x is equal to C6 sine alpha x. Alpha is n times pi. So we have x of x is equal to sine C6 sine n pi x. Now we have to find t of t. At the beginning we found equation for t, so equation for t was t double prime plus 4 lambda t equal to 0. T double prime plus 4 lambda t equal to 0. And we know lambda is alpha squared, so as a result we have t double prime plus 4 alpha squared times t equal to 0, and we can solve this equation. So t of t would be equal to we used C6, so now we have C7 cosine 2 alpha t plus C8 sine 2 alpha t. We also found alpha, so alpha is equal to n times pi. As a result, t of t is equal to C7 cosine 2n times pi t plus C8 sine 2n times pi t. So now we have x of x and we have t of t, so we can use u of x and t, because at the beginning we said u of x and t is equal to x of x times t of t. So it's equal to x of x, we found it, it's C6 sine n pi x, and t of t, we found it, it's C7 cosine 2n pi t plus C8 sine 2n pi t. So this solution is valid for all the values of n. As a result, I say we have un of x and t. It's equal to, if I multiply C6 by C7, I'm going to have another constant, so I call it an. So it's an cosine 2n pi t plus, if I multiply C6 by C8, we're going to have another constant, I call it bn. So it's bn sine 2n pi t and it should be multiplied by sine n pi x. So we could find un of x and t based on superposition principle. Summation of un would satisfy partial differential equation and boundary condition as well. So we say u of x and t is equal to summation of un n from 1 to infinity, and it's equal to summation of an cosine 2n pi t plus bn sine 2n pi t and it's times sine n pi x. Now we have to go and check if u of x and t satisfies initial condition or not. So the first initial condition that we have, it says that u of x and 0 is equal to sine pi x. So the initial condition says that u of x and 0 is equal to sine pi x. Now I plug 0 in our solution in our u of x and t. So u of x and 0, it's equal to summation of an times cosine 2n pi t, so t is 0, cosine 0 is 1, plus bn times sine 0, so sine 0 is 0, and we have sine n pi x, so it's sine n pi x, and based on the initial condition, this series should be equal to sine pi x. We have to find an now, so in order to find an, you can use half-range series. The formula is in the formula sheet, you can easily find it, but I don't want to use half-range series. I just want to expand it, expand u of x and 0. So in fact, u of x and 0, it's equal to summation of an sine n pi x. If n is equal to 1, we have a1 sine pi x, plus if n is equal to 2, we have a2 sine 2 pi x. N equal to 3, we have a3 sine 3 pi x, and so on. And it should be equal to, based on initial condition, sine pi x. If you compare right hand side of equation and left hand side of equation, in right hand side of equation we have sine pi x, in left hand side of equation we have a1 sine pi x. As a result, in order to make them equal, I assume that a1 is equal to 1. If a1 is equal to 1, we have a1 times sine pi x is going to be sine pi x, and it's equal to right hand side of the equation, and I assume that a2 is equal to 0, a3 is equal to 0, and so on. So in fact, I assume that an is equal to 0 for all the values of n, but n cannot be equal to 1. For n equal to 1, we have a1, which is equal to 1. Based on this assumption, right hand side of equation is equal to left hand side of equation. So we could find an using this technique. Now we have to go through the second boundary condition, second initial condition to find bn. So we have second initial condition. Second initial condition says that derivative of u with respect to t at t equal to 0, it's equal to sine 2 pi x. So derivative of u with respect to t at t equal to 0, it's equal to sine 2 pi x. Now I take derivative of u that we found here. So derivative of u with respect to t, it's equal to summation of. So summation of an cosine 2n pi t is equal to minus an times 2n pi times sine 2n pi t plus derivative of bn sine 2n pi t is bn times 2n pi t 2n pi times cosine 2n pi t, and it's all multiplied by sine n pi x. N is from 1 to infinity. Based on initial condition that we have here, so the initial condition says that derivative of u with respect to t at t equal to 0 should be equal to sine 2 pi x. Now I plug 0 in this equation. So derivative of u with respect to t at t equal to 0, it's equal to summation of n from 1 to infinity. So we have an times 2n pi times sine 2n pi t. So sine 0 is equal to 0. This term is gone. So here we have bn times 2n pi times cosine 2n pi t. So cosine 0 is 1. So as a result, we have bn 2n pi cosine 0 is 1 times sine n pi x. Based on initial condition, this guy should be equal to sine 2 pi x. Again, for finding bn, you can use half range series, but I'm going to expand it again. So if I expand du over dt at t equal to 0, we're going to have, if n is equal to 1, we have b1 times 2 times 1 is 1. So it's going to be 2 pi sine n is equal to 1 pi x. If n is equal to 2, we have b2. 2 times 2 is 4 pi sine 2 pi x plus b3. So 2 times 3 is 6 pi sine 6 pi x, sorry, sine 3 pi x, plus and so on. So it should be equal to second initial condition, which is sine 2 pi x. Again, I compare right hand side of equation with left hand side of equation. Here we have sine 2 pi x. So in left hand side, at first we have sine pi x. We don't like it. So here we have sine 2 pi x. As a result, I assume that b2 times 4 pi is equal to 1. And I assume that b1 is equal to 0, b3 equal to 0, b4 equal to 0, and so on. If b2 times 4 pi it's equal to 1, so it means that b2 is equal to 1 over 4 pi, and bn for all the values of n is equal to 0, but n cannot be equal to 2. Why? Because we already found b2. b2 is 1 over 4 pi. Now we have an, we have bn, so we can easily find u of x and t. So we had u of x and t is equal to summation of an cosine 2n pi t plus bn sine 2n pi t, and they are all times sine n pi x. Let's expand it. So if we have u of x and t here, so it's equal to, if n is equal to 1, we have a1 cosine 2 pi t plus b1 sine 2 pi t times sine pi x, because n is equal to 1. Now we assume that n is equal to 2. If n is equal to 2, we have a2 cosine 2 times 2 is 4 pi t plus b2 sine 4 pi t times sine 2 pi x. If we assume that n is 3, so we have a3 cosine 6 pi t plus b3 sine 6 pi t sine 3 pi x, and so on. So it's the solution of u of x and t. So u of x and t is equal to. So we know that we found a1 is equal to 1. So as a result, we have cosine 2 pi t. b1 was equal to 0 times sine pi x. The second term, a2 is equal to 0 because we know that a1 is equal to 1. an is equal to 0 for all the values of n when n is not equal to 1. So as a result, a2 is equal to 0. b2, we found it here, it's 1 over 4 pi times sine 4 pi t times sine 2 pi x plus a3. a3 we know is equal to 0, b3 equal to 0, a4, b4, they are all equal to 0. As a result, we could find u of x and t as cosine 2 pi t sine pi x plus 1 over 4 pi sine 4 pi t sine 2 pi x. Now the problem asks us to find displacement of string. So in fact, we want to find u of x and t at a given point. So you want to find displacement at point 25 and at t equal to 0.2. If you just plug x and t in u of x and t, so you can find displacement at this point equal to 0.265. So we could find displacement and we solve this problem.